analysis of variance. Suppose that instead of just two groups that we're comparing, we had a whole bunch of groups. Now, I suppose we could do them pairwise, but there are lots of pairs. With four groups, you could have John and Paul, John and John and George, John and Ringo. You could have Paul and George. You could have Paul and Ringo, or you could have George and Ringo. So there are a total of 6 different groups, 6 different pairwise. If you added a 5th member, then there would end up being 10. Now, suppose that you were doing a 0.05 t-test. If you ran 6 of them, you'd get each pair right 95% of the time, but the odds of getting all 6 of them right would be 0.95 to the 6th. So that means that if nothing was going on, you'd still believe that something was going on over 1/4 of the time. With 5 groups, you'd believe that something was going on more than 40% of the time. And that's just too scary, because you no longer have the sense of 0.05 being the probability of saying something that's false. We're really concerned about doing these one pair at a time. And 4 or 5 groupings is nothing all that large. I've seen analysis of variance done with over 20 different groupings. So you need a new technique. Now, the formulas for analysis of variance. There's a difference between what's happening between the groups. How much does this group differ from the other 3? And how much difference do you find within the group? How much natural variation is present inside of each group? So here you'll notice I call it the score minus the average for that column. So here the average would be higher than it is here, for example. So you'd take the average from within the correct column, and you'd take the score minus its natural average, and you'd score the result. This symbol, x bar bar, it's not quite the average of the averages, it's the grand average. It's the average of all of the numbers. So if I take the individual means for each group and compare it to the overall mean, squaring the result, I get a sense of how much variation is present between the 4 different groups. Degrees of freedom. For between, if I have 4 different groups, then the number of groups k would be 4. Degree of freedom would be 4 minus 1. So here I'd have a degree of freedom of 3. Here, n minus k. So it turns out I've got 20 numbers here, 20 data points. 20 minus 4 would be 16. Mean squares. In both cases, you take the sum of the squares and divide it by the degree of freedom. The F statistic. This is going to be our test statistic. It's a lot like Z or T, or we used R in some ways as a test statistic. With chi-squared was a test statistic. So this is going to be a test statistic. What we're looking at is how much variation is present between the groups and comparing it to how much variation is within the groups. If the groups are cohesive within, but different from each other, then F would tend to be high, because some of the square between would be high, some of the square within would be low. On the other hand, if there's a lot of variation within the groups, then we can accept a small amount of variation between the groups. The cutoff line is if f is larger than 1, you suspect that maybe something is going on. If f is smaller than 1, then it's unlikely to. Fortunately, we have the calculator to figure out all of these values and to figure out the probability. What you're going to be doing is making a report. The report is going to include a table like this: between, within, total, SS, sum of the squares, degree of freedom, mean squares, F statistic, and your calculator will also tell you the probability. I'm going to have a null hypothesis, an alternative hypothesis. I am going to set alpha. Let's just make it 0.05 out of convenience. For the null hypothesis, well, the null hypothesis is going to be that the means are all the same. That mu sub 1 equals mu sub 2 equals mu sub 3 equals mu sub 4. I went up to 4 because I have my 1, 2, 3, 4 categories. The negation of this is not going to be the same thing with a bunch of not equal signs, because it's possible that mean 1 and mean 2 are the same, that mean 3 and mean 4 are the same, but that this group is not the same as that group. It's possible that 1, 2, and 4 are all the same, and it's 3 that's different. All we know, and this is going to be your alternative hypothesis, is that if it's not the case that all the means are the same, then at least one mean differs. So this is going to be your null hypothesis. Go up to however many groups you have. This is always your alternative hypothesis. Next, the calculator work from scratch. So stat, edit, let's get rid of these values. And for John, 18, 22, 19, 20, 20, 21. For Paul, 15, 19, 20, 23, 18. For George, 14, 16, 12, 12, 11. For Ringo, 20, 8, 9, 19. If you're doing this along at home, I'll just put this up. You can pause if you'd like, and let's proceed. When we run the test, the most remarkable thing is how little happens. Stat, test, if you go up 1, you see ANOVA. That stands for Analysis of Variance. Kind of an acronym. Analysis of Variance, or ANOVA. When I hit enter, all it does is say that it's ready. It doesn't do anything else. In the previous ones, you had a menu to navigate. This time around, you have to tell it what to do. Fortunately, telling it what to do is simple. You just tell it the 4 lists that you used. So you used list 1, comma, list 2, comma, list 3, comma, list 4, close parentheses. Tell it the lists and then just hit enter. So, let's see what we have. There are some things to explain. Between and within are the terms used in the social sciences. I stick with them because they end up being the ones that make the most sense. they kind of explain what they're doing. Instead of between, you'll often hear it referred to as the factor or the treatment that is used. But factor and treatment don't make as much sense to me as thinking what's happening between the four different groups in this case. So factor, degree of freedom is 3. Sum of the squares, I'm not going to be fussy on this, so I think just taking it down to integers is fine. 189. Mean squares would be 63. So when we get to f, our numerator is going to be 63. It does mention f and p. I might as well write them down now. F is going to be, it's a test statistic, so please 3 decimal places, 5.544. P is going to be 0.0084. 2 decimal places here, or sorry, 2 significant figures here. I'm not counting the initial zeros, I'm only counting once I see something that's not a 0. When you go down, instead of within, it might be a little bit disorienting what the calculator calls it. They call it error. The most sense I can make of this for you is if you think of just background error, if you think of noise in the signal, that's what is happening within. That's what's making it more difficult to figure out what the mean for the different groups is, because you have a margin of error for it. But when it says error, that stands for within. So on your calculator, between is factor, within is error. The degree of freedom is 16, as we mentioned before. 3 plus 16 is 19. That happens to be n minus 1. The sum of the squares is 182. So the sum of the squares is comparable, but I'm dividing by a much larger number. So 182 over 16 is about 11. And 63 over 11 is about 5.5. I'm only precise with the f. I do like adding these two numbers together. That's going to be 371. If you take more statistics classes, they will often give a description of what's going on in between in terms of how large this number is in comparison to this number. So, P is 0.0084. That is less than 0.05, which was alpha. Therefore, we are going to reject the null hypothesis. So it's a very simple test to run. Unfortunately, the conclusion leaves something to be desired. The conclusion is just at least one mean differs. So the natural question is, which one? At the higher level, you run these on statistics packages which have what are known as post hoc tests. The calculator doesn't have one of those. The one that I tend to use is known as Tukey's, and it ends up being very similar to something that we've been practicing, stacked t-intervals. This is why on test 1 I had you do stacked box plots, and on test 2 I had you do stacked t-intervals, also that the second half of this problem will make sense. Notice that I'm marking it as 3/4. That's because this whole problem, the top half is going to be worth 10 points. The bottom half is going to be worth 10 points on your test. Let's go for the bottom half. So, our 4 groups, I could call them 1, 2, 3, and 4. I'm tempted now to call them John, Paul, George, Ringo. I'm going to have the confidence interval. I also want X bar, and then I want the stacked t intervals. So I've got a bunch of these to do. If alpha is 0.05, we use the 95% confidence interval. Fortunately, they are quick. First, stat test 8, data, enter. List 1, enter, 0.95, enter, and calculate. So I am getting 18.5 to 21.5. I'm also interested in X bar. The calculator says 20, but since the raw data had 0 decimal places, I add 1 decimal place, and I'm going to call it 20.0. Next, I do the next one. If you get into a rhythm, these are really quite fast. Stat, test, 8, down, switch, list, down, 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 enter. And 15.4 up to 22.6. The mean was 19 even, but again I'll call it 19.0. Next, stat, test, 8, down, switch list, down, 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 enter. 10.5 to 15.5. The mean was 13.0. Last, Ringo. Stat, test, 8 for the t interval. Down, switch list, down, 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 calculate. 3.9 up to 24.1. And the mean was 14. Now, calculator away. Look for the smallest value. That would be the 3.9. The largest value ends up being the 24.1. So, when I make my bar, I think since 3.9 is close enough to 0, I'll start there. I'm tempted just to go out to 20. Half of 20 is 10. So here's 5, 15, and that leaves me with a 25. 18.5 to 21.5. So I'm looking at something in this region. 15.4 to 22.6. So something in that region. 10.5 up to 15.5. So I'm looking at something in that region. Do these overlap? I mean, visually it looks very close. This one goes up to 15.5. This went down to 15.4. So ever so slightly, there is a small zone of interlapping there. Last, 3.9 out to 24.1. So, what overlaps and what doesn't? Well, Ringo overlaps with all of them. We saw that Paul and George do overlap, but just barely. In this case, there's only one. Often there are more, but there's only one that doesn't overlap. George, the mean for George could be For the sample, it was 13, but for the population, it could be as high as 15.5. For John, it could be as low as 18.5, but that means that John's is clearly larger than George's. So, either use 1, 2, 3, 4, or in this case, JPGR. I am going to say that the mean for George is less than the mean for John, and that's the only one that I can point out. Now, what is it that makes some of these bars long and some of them very short? There are tendencies, and it all comes down to understanding the t-interval. If you don't have much data to go by, then the bars tend to be larger. The law of large numbers tells us that as n increases, the t-interval should tend to decrease. The other thing is if the numbers are packed closely together, if there's not a lot of natural variation, then the bar tends to be smaller. The more variation, the bar tends to be larger. If you look at John, smallest was 18, largest was 22. That was a spread of just 4. Now, John did have one extra data point than Paul did. But do you see the spread here from 15 to 23? That's a range of 8, double the range for John's numbers. There was more natural variation in Paul's scores than in John's scores, and that's why even though Paul had a lower mean for the sample, we couldn't narrow it down. It could even be that Paul's mean was above what John's mean could plausibly be. So greater variation, smaller variation, slightly larger numbers. Ringo, of course, had the longest bar, and the reason why should be somewhat obvious. Look at just two different features. First, the range, 8 to 20. That's a range of 12. So that's going to be 3 times as much as John's. Next, numbers. Now, when we get down to this few numbers, the difference between 6 points and 4 points is really starting to be important. If it was 16 and 14, the sample sizes would have been more comparable. But 6 and 4, Ringo just had a small sample. The numbers were all over the place. It's not surprising that the t-interval kind of throws up its hands and says somewhere in here and gives a very broad range, including a number below any that Ringo scored and above any that Ringo scored. So expect some bars to be shorter, expect some bars to be longer. 20-point problem, 10 points for the first half, 10 points for the second half, and please include all of this information, the confidence intervals, the mean, the stacked t-intervals. Have a good scale, and include any judgments. In this case, there was only one.